Oh, I completely forgot that I bought a new tea. Forgot to bring it in here. Just a second. Just a second. Is какой looking this? It's some sort of a. I don't know what brand it is. They didn't pay me for showing it, but it's just like some sort of maybe Russian brand. But it's the only brand that I more or less like, and it's available in the near store. So I kind of just buy it all the time. So yeah, it's Earl Grey. It's nice. It tastes nice. Earl Grey tastes nice. So welcome everyone to a nightly stream. Right, so I was trying to not do any work and just go to sleep a little bit earlier, but I don't want to talk about it. It is what it is and it isn't what it isn't. So my body's so good used to the nightly streams that I just literally cannot just like live a normal life at this point, I suppose. I don't even have a place where I can throw it away. My god. So, on the nightly streams, we actually started to work on our own immediate mode GUI library. So you can find this library in the description. I'm gonna put it into the description just for you. So yeah, here's the source code. Okay. There we go, here's the source code. And if you never heard about immediate GUI libraries, I would highly recommend you to take a look at the original one that inspired this entire series of streams called IamGUI, right? I would really recommend you to check it out, so I'm going to put it in the description as well. And so we recently watched a talk by Casey Handmade Hirotori, who basically like inspired this entire idea of immediate GUI, and you can find his talk on YouTube. I think YouTube is going to recommend me right now because we recently watched it on the stream. No, it doesn't recommend me. Okay, so you can always find it by Casey Muratori. Immediate. I absolutely love how every time I search for Casey Muratori, the first thing that pops up is rant. It's just absolutely beautiful. Yeah, he's a ranty guy. What can I say? He's a ranty guy. So that's the video I'm talking about. Alright, so, and I'm gonna put it into the description as well. Okay. Casey Muratori. IamGUI. Right, so there we go. So all of that is going to be available for everyone. Alright, and so the reason why we're doing all of that, why we're developing our own library, is because we want to learn about immediate GUIs, right? So that's the entire purpose. Alright, let me make a cup of tea and we're going to start doing all of that. Oh, you want to see something? Something funny. I was preparing for the stream and so one of the problems that I have while recording all of the streams is that the final file tends to be very big and I don't really have that much space on my hard drive, right? I only have 7 gigs, and I was looking around trying to find what to remove from my machine, and obviously I went to my main folder where I do all of the development, and I wanted to look like, can I delete something from there? So what's the accumulated size of this entire folder? And it's 8.6 gigs. I thought to myself, well, okay, so it's an accumulated size. What is the biggest folder in there? So let's actually go a little bit deeper. Actually, one depth, right? One layer depth, and I sort all of that by numbers. So the biggest project in here is Rust line counter. Okay, if you go into Rust line counter and take a look at its like accumulated size, it's 5.1 gigs. Like What the fuck? A project that is called Rust Line Counter doesn't sound like something that should take up 5.1 gigs. And I was looking into what the hell is that, and I found a folder called data, and it's just filled with these kind of files. I do kind of vaguely remember this project. I think we did it only, I don't know, I think we did it on a New Year, and it was just a random bullshit project. So we just implemented a program in Rust that counts lines, and it just generated a bunch of data to actually have something. It's just compare performance or something like that. And yeah, the size of this entire folder is like, yeah, I can just remove. So here's the available space in home. I just remove this data, and instantly how much I've got. This is not how we check it. 13 gigabytes. Nice, nice. Now I have enough space. I don't know. Anyway, so let's make a cup of tea. Let's make a cup of tea. Let's make a cup of tea. So today I wanted to do a very special thing. Today I wanted to implement text for our UI framework. Right, we already have buttons, le buttons that are clickable. You can click on them, you can register the clicks, you can do things when you register the clicks, but it's kind of boring. There's no text in there. So let me show you how the UI looks like right now. So if I try to run it, there we go. So you have 5 buttons. As you can see, they interact with the mouse. You can hover over them, you can click on them, and yeah, they register. But I'd like to have some text over them, and that's precisely what we're gonna work on today. Hopefully it's gonna be super fast stream. I just want to add a basic, very simple font rendering. Basic, very simple font rendering. All right, so I'm gonna go to the kitchen, turn on the kettle, and then I'm gonna be back, and we're gonna start doing all of that. Don't go anywhere, it's gonna be super fast. So yeah, everything's fine. Everything's fine. All right, so I'm going back. All right. One special thing about our UI library, not only ours, but I think IMGUI is implemented in a very similar way. It has a portable graphics API agnostic way of rendering itself. So basically, it doesn't even know how to render to this window. The library itself doesn't know how to render itself to the window completely, and this is what makes it interesting. So essentially, let me find it. It renders itself into 2 buffers, the buffer of vertices and the buffer of triangles. Right. So a vertex is a combination of vector, 2D vector, and the color. So it's some particular vertex with associated color. And triangle is a triple of unsigned integers, basically the indices in the vertex buffer. So essentially how the UI renders itself, it just generates a bunch of triangles into the memory. So it has a chunk of memory, and when it needs to render itself, it just fills up it with triangles. Your job as an integrator of this library to a particular graphics API is to take that buffer of triangles and render it with the graphics API of your choice. You can do it with OpenGL, Direct3D, Metal. You can draw triangles directly in a frame buffer if you want to, but this thing is sort of optimized to work well with such graphics APIs. OpenGL, Direct3D, Metal, you know, the usual GPU things. So that's what makes this kind of rendering interesting. So I think my tea is ready. I'm gonna quickly go to the kitchen and pour myself a cup of water, and I'm gonna be back. So don't go anywhere. All right. And the easiest font rendering that you can implement is usually bitmap font rendering, right? So there is a particular bitmap font that I keep using on all my projects as a placeholder because it's so goddamn simple. I absolutely love it. It's a bitmap created by somebody with a nickname Domson. Right, so yeah, he actually uploaded a couple of his fonts, actually not a couple, but 3 of his fonts to OpenGL Art, and they're absolutely genius. I absolutely love them. So they're so simple, and it's so easy to implement some sort of like rendering system for them, right? So they have even sizes, and just by ASCII code, you can precisely find its place in this table and just cut it out and render it, right? So obviously I'm gonna give the link to all of that in the description. So I'm gonna put it in here. So there we go, it's in the description. And I wanted to integrate this thing, but here's the problem. Bitmap font is like, it's rendering the pixelated image, so we're working with pixels. But our library can only render triangles, right? So it's more of a vector graphics rather than the raster one, right? So how can we even implement all of that? Well, we can try to interpolate the pixels with the triangles. Why not? So essentially, if you have a particular, like a bitmap font thingy, right, so imagine that you have pixels, a couple of pixels, actually like some sort of a texture, 2 by 2, right, and some of the pixels are transparent, but some of them are filled in, right? And you need to render it in our portable display that can only render triangles. How would you do that? Well, you would basically render these 2 quads as triangles, right? So basically you will just interpolate all of that with triangles. And what's cool is that it's actually like easy to scale this kind of stuff. You just scale the triangles and yeah, it will just work. So I was thinking maybe we can implement the font rendering, but render the pixelated fonts, render the pixels with triangles. So yeah, what do you think about this idea? In any case, I'm implementing that, so it doesn't matter what you think about it. Whether you like this idea or not, we're implementing it. And that's precisely what this stream is all about. All right, so let me pour a cup of tea. So how are we going to be implementing that? First, we need to get the font into the program, right? We can put it along with the program as a file, but that is not convenient because I wanted to implement my immediate GUI library as a header-only library that consists of a single file, so it's easy to integrate into your C++ application. So one of the things we can do we can take the bytes of the font, right? We can take the bytes of the fonts and we can turn them into a C array, and we can copy paste them into our source code, so we can use them in our source code. So I already did that actually before. I already did something similar to that before. TSMR, by the way. TSMR. Obligatory salt, of course. Beautiful, absolutely beautiful. All right, so some time ago I worked on a project called Rust Browser Game. It's a very interesting project, and I really liked it. So essentially I would implement there is a description here. So the idea is to make a simple game in Rust as bloat-free as possible, only using Rust C. This could be achieved by using WASM32 target directly and developing an embedded style. So the idea was the following. The entire logic of the game is contained within the module, the WebAssembly module, that renders the frames into its own memory. Right, then the JavaScript side of things actually takes that memory and interprets it as the image data and renders those frames into canvas. So the entire scheme of how it works is actually described here. I wonder if I can zoom out so you can see everything in here. Yeah, as you can see, this is how it works. So here's a WebAssembly logic. It renders itself into display, and then the browser takes those frames from the memory and puts them into image data and just HTML canvas and stuff like that. That's a very interesting project, and it's actually turned out to be extremely portable. So we managed to port it to all sorts of things. We managed to port it to SDL, to Ncurses, and to UEFI. So you can find links to all of these projects in here. It's actually very interesting. I really recommend to check it out. I'm going to put it into the description, right? I'm going to put it into the description. So the thing about this project is that it uses the font rendering, and we're using the font from Domson, right? How we did that? Well, we did precisely what I described. We actually copy-pasted, we embedded that font into the source code. But look how small it is. Look how small it is. We basically compressed it with our own custom algorithm. There's nothing particularly magical about that custom algorithm. It's just like a very special algorithm that is optimized specifically for that font, and it works really well only for that font and nothing else. So yeah, I think like you can read more about this kind of algorithm in a separate repo. So I created a tool that consumes these font files and it compresses them. So yeah, here's the interesting thing. So the original PNG size is 1 kilobyte, but we pretty consistently can actually compress it down to 620 bytes, which is kind of cool. So it was important for the game. Because we wanted to implement a bloat-free game. But then I'm thinking, it's also kind of important for header-only libraries too, because you don't want to like include like thousands of bytes there as well. So because you want to make you want to keep your header files compact. So maybe we're going to use the same approach for our header library. So yeah. So essentially, this tool is relatively simple. You just feed it one of these sprite sheets of the fonts, and it can generate you either binary format, or it can generate you Rust and a recently added C code. It can generate you like literally like takes an image and generates you C code that you can copy paste it in your code, but then you'll have to implement decompression of that font. Right, so let me demonstrate you what I mean. So let me fetch the other stuff. So okay, so I'm gonna merge the latest thing that I actually fetched in here. So here they are, and I probably need to recompile everything just in case. Did I put that in the description? I think I put it. Okay, so it takes some time because I'm also streaming. Right. All right. So, and if you try to run this this tool, it accepts the PNG file, but also it lets you choose one of the formats, right? So if you just run it on which one? I kind of like old school one. So if you run it on charmup old school, it will generate you Rust code, right? It will generate you just Rust code. But our project is in C, so we can say something like -f C, and as you can see, it generated us the C code. I hope this is a compilable C code because I actually never tested it. So one of the things we can do, we can just now take this code. We can just take this code and copy paste it into our thinking, into our project. So where do I want to put it? I'm going to put it somewhere here. It doesn't really matter. Alright, so this is a compressed font, and here's the disclaimer, and yep, so the entire image of this old school font, right, is compressed within this amount of characters, right? So the next thing we'll need to do, we'll need to decompress all of that. So the interesting thing about that font is that it has fixed size and only 2 colors. It's a monochrome font, right? It's a monochrome font. We can try to prepare some memory. I can try to prepare some memory for the font, and I'm thinking, so this one is actually not static. I think this kind of thing has to be always marked as static. Let's mark it as static. So let me see if this entire thing compiles. So it's going to be -b. So static is not at the beginning of the declaration. I think it wants us to do something like this. Yeah, this is precisely what it wants us to do. And the question is like, where are we gonna store the uncompressed version? Where are we gonna store the uncompressed version? I'm thinking to actually store it inside of the state of the user interface. So it's like the access to the entire thing is more or less like thread safe if you're going to be actually having like separate threads like for UI or for something else. But yeah, but uncompressed version doesn't really matter because it's constant and you shouldn't be able to even modify it. It's just sort of baked into the constant chunk of memory, if there's such thing at all. So yeah, let's actually put something like this in here. We're gonna have a font, right, and we're gonna have a predefined font width and predefined font height, right, and a single pixel of that font is gonna be unsigned character, right, because it's a monochrome font. So now let's define the sizes of the font. So font width, as far as I know, the Thompson fonts are 128, and in terms of the height, I don't remember what's their height. What's their height? 64. Yeah, it is in fact 64. There we go. So now I think we need to implement some sort of a function that accepts the state of the UI and fills up this entire thing. It just fills up this entire thing, uncompressing that font. The compression and decompression algorithm is actually relatively simple, so I think we would be able to implement it on the stream. So let's put something like this: unsigned, I'm HUI, uncompress font, right? And we're gonna accept the state of the UI. We're accepting the state of the UI, and we're gonna be putting all of that stuff in there. We're gonna be putting all of this stuff in here. Okay, so the compression algorithm here is very straightforward. So it consists of two phases, right? It consists of two phases. So the first phase is actually you take a monochrome image, which consists of sequence of bytes 0, FF, FF, and so on and so forth. So it's just basically different combinations of like 0, 0, FF, F, and so on and so forth. 0 means black, FF means white. So essentially what we do is we take these bytes as chunk of 8 and we turn them into a single byte, right? So essentially for each of these bytes, we basically compress it into a single bit. Instead of using bytes, we're using bit. So that means that way we can cut down the size of the entire font by 8. So, but then it creates an interesting problem. So because of the background color, there is a lot of strides of zeros, right? It compresses really well, right? It compresses down to 1024 bytes. Because of that, without any special compressions of PNG or anything like that, it just compresses to that. But then you have these strides of zeros. So, and to get rid of these strides of zeros, we apply the second algorithm, which is basically RLE, right? So it stands for run length encoding, but we apply it only for zeros. We apply it only for zeros. I think I can even demonstrate that. I think I can even demonstrate what I'm talking about. If I go to the font gen thingy, right? If I go to the font gen thingy, and we apply two compression algorithms in here. So let me get rid of this entire thing. So where do we apply compression? So yeah, there we go. So it's kind of interesting. I can simply do compressed bytes. It's gonna be that, and I wonder if I can just run it. Can I just run it? Okay, and then after that I can do just something like char map old school PNG, and there we go. This is the completely uncompressed version of the font. This is how it looks like when it's monochrome. It's just like zeros and Fs. You can cut down the size of this entire thing by 8, right? And that's precisely what we do on the first step. So by doing compress monochrome pixels into bits, right? So this is the first step that we're doing here, and we can take a look at what exactly going on in that step and how much it compresses it. It compressed it really well down to 1024, as you can see. But again, as I mentioned, there's like huge strides of zeros, right? And because of that, we apply a special RLE algorithm. But it's actually very interesting. So it's only zeros that form these stripes. If it's not zero, it's usually quite unique, right? It is usually quite unique, and if it's not unique, there's quite rarely several of them. So essentially, we compress it into the following algorithm, right? So how are you supposed to uncompress it? You look at the byte, and if the byte is 0, the next byte is the size how many zeros to uncompress it to. If the value that you're looking at is not 0, you just interpret it as is and you just leave it as is. So this is basically what we compress it down to, and this is how we manage to get rid of these strides of zeros. Okay, so again, if we just apply both of the algorithms here, we manage to compress it down to 622 bytes. So this is basically both compressing bytes into bits and applying RLE. So yeah. So maybe I'm gonna actually put the link to the article about RLE in the description for anyone who's interested. I don't know, maybe it is interesting for somebody, maybe it is not. I'm not quite sure. Maybe I'm putting too much stuff into the description. You tell me, maybe I just like overflow my description with links and this is not something that you want to go through. Anyway. I need a little bit more tea. I just need to sip my tea. All right, so we have this array, and we know the size of the uncompressed array. We just need to, you know, uncompress everything. We just need to uncompress everything. We could steal the uncompression algorithm from a Rust browser game, because we already did that, but that means I'll have to convert it from Rust to C. So that's one thing I could do, or I can try to implement it from scratch yet again. Why not? Doesn't sound like a bad idea, to be fair to me. Doesn't sound like a bad idea. Anyway. So let's start. I'm gonna start iterating through compressed font. I need to know the size of the compressed font. Maybe we can actually put that size somewhere here. So compressed font size, and it's gonna be 622. So compressed font size. So this is our compressed font size. So uncompressed font. And we're going to be uncompressing it by just iterating through the compressed bytes and interpreting them and just doing something about them. All right, so I'm starting from 0 up until compressed font size. And here is two situations. Your current byte is either equal to 0 or not equal to 0. Right. If it's not equal to 0, that means you just append it to the font currently. So if you want to append it to the font, you need to keep track of the size of how many bytes you already appended into that buffer, right? So that's what you need to do. So let's introduce the following thing. It's going to be something like size t, font size, and it's going to be initially 0, right? So, and essentially, you just need to append that that byte into the font. But this is not necessarily true, because a single byte contains 8 pixels. Yes, it contains 8 pixels. So that means you need to iterate through the bits of that byte and append the pixels. That's what you need to do. Yes. Yesu, кого fucking десу. All right, so your byte is not 0, so you iterate through the bits. So it may bit from 0 to 8 plus bit. Okay, so then you take the compressed font, and I don't remember in which order we have to actually extract them. It depends on how we compress everything. Man, I really need to actually grab the decompression algorithms and put them into the DOMSON FontGen repo, so you can just copy paste them and don't have to implement them yourself. That will be actually kind of convenient. So the tool compresses the fonts and comes with the source code to decompress it for you, to embed it into your program. I think that would be actually kind of cool. But anyway, so when we're compressing monochrome pixels into bits, right, how do we compress them? We actually, oh yeah, so we actually pushing them to the left. So we shift all of the pixels to the left, add 1 bit, then shift to the left 1 bit. So that means the first one is the most significant one. Right, the first one is the most significant one, so that means we have to do a special trick. So we're iterating them from 0, but maybe we have to iterate them from like 7, maybe 8, until it's like greater than 0, right? So until it's maybe greater or equal, yeah, until it's greater than 0, and we're going to be actually subtracting the bits. So it's going to be from 8 to 1, right? From 8 to 1. And here we're going to be actually shifting to the right, but with -1, right? And the reason why I'm actually not doing it from 7 to like you know, equals to 0 is because size t is unsigned, so this is kind of a dangerous loop that may never actually finish. So you have to sort of like shift it to the left by 1, if you know what I'm talking about. I hope we didn't make any mistake in here. Right. So, all right, I'm shifting the bits, and then I'm extracting that bit, right? I'm extracting that bit, and if that bit is 0, the pixel that we push into the font is going to be a 0, and if it's 1, the pixel that we push into the font is going to be 0xFF. Right, so that means we can use this as a factor, as a multiplier, right? So we can use it as a factor, as a multiplier, and then we're just pushing that into the IMHUI font. So it's going to be font size ++, and there we go, we just push this entire thing in there. I hope I didn't make any mistake, and if I did, it's going to be very, very painful. All right, so... Interestingly enough, you have to be super careful, because if there is some malformed data in the compressed font, you might actually end up uncompressing too much. So we want to kind of assert that the font size is less than font width multiplied by font height, right? So we kind of want to assert that. To be fair, we'll have to do that every time we're modifying font size, so it would be better to have some sort of a function that keeps track of that or something, or I don't even know. But to keep track of that, you have to keep track of the font size, and the font size is kind of intermediate thing that you don't want to store in original state. So I'm not sure how to implement that, but I'm going to keep it as it is. Anyway, so we handle the case when the compressed byte is actually not 0. All right, let's handle the case when it's actually 0. So when it's actually 0, we have to look at the next byte. Right, we have to look at the next byte. So we need to assert that the next byte even exists. So I+1 has to be less than compressed font size, right? And if the data is malformed, this assert will fire up, and this is how we will know that something is going wrong. So this kind of stuff is usually checked at runtime in Rust, but we are programming in C, so we have to check it ourselves. The easiest way to do that is with asserts. Maybe it shouldn't be asserts. Maybe in the production code it has to be actual checks that maybe do something like something smarter than this, but we're gonna keep it like that for now. So we know that the next thing exists. We know that the next thing exists. That means if we take the next sort of byte unsigned char n, compressed font I+1, this will indicate how many zeros we have to uncompress. But that's not enough. That also indicates each 0 is actually 8 pixels, right? So you have n bytes multiplied by 8, and this is how many pixels you have. So but one of the things we want to do, since we're expanding them to 0, I think it would be way easier to actually memset the entire thing to 0, right? Size of to 0, like this. I think this is how you use memset. I'm pretty sure that's how I use it. Maybe not. Let me double check. So first you set the pointer, then you set the value that you want to fill it with, yeah, constant C, and then how many bytes you want to fill. So I think that's pretty much what it is. Okay, so we can assume that font is initially filled with zeros, right? That means expanding the zeros is a pretty trivial thing, basically changing the font size, changing the count, the pointer at the of the end of the font, right? So that means we'll have to do something like font size plus n, but not only n, but multiplied by 8, right? So, and again, we probably have to also assert that after that font size is less, and this time it could be even equal to font width, font height, right? So we want to assert that and make sure that everything's okay. All right, but on top of that we also have to update I, because since we like took the next one, we have to do something like I+1 too, right? Maybe we can even do it somewhere here. right? So I plus 1 is that. Maybe we can do it like this. So we increment I, then we check again that I is less than the size, and then we take I as the n, we increment that, and there we go. We implemented the decompression algorithm for our font. This entire thing must be part of the Donson font gen tool. So you don't have to like implement it yourself. You could just copy paste it from there. But I don't know. I haven't come around to actually put it into the source code, so whatever. All right, so let's see if it compiles. Maybe it doesn't compile. But if it compiles, it must work, because you know what we say in the industry: if it compiles, it works. Well, but it doesn't compile. Okay, so this is because memset is available in string.h. That's why. And I guess that works, surprisingly. So uncompressed font. Let's actually make it non-static and available outside of the implementation, right? And this is because I want to test how it works, right? I want to test how it works and just see if it fails or not. So I'm going to go to the main program, and so these are shaders for rendering and stuff like that. So we have a lot of OpenGL magic going on in here. Don't get scared. I'm scared myself. So let's comment out the main entry point, and let's create an alternative one. In the alternative entry point, I'm going to create the state of the UI, preferably in a static memory, because it could be big, right? So, and everything is filled with zeros. And the next thing I'm going to do, I'm going to call this function to uncompress the font, right? I'm going to call this function to uncompress the font, right? And let's just see if it failed or not. We can also try to print the font, but I mean, printing just the bytes doesn't really give you that much of an interesting information. So we can just run it and see if it does not segfault or anything like that. Or at least it doesn't trigger any of the asserts. We have like at least 3 asserts in here. So if something goes wrong, they will fire up and we will know about that. So we're doing a pretty defensive software development in here, all right? So let's just run it, and it didn't fail. It actually exited successfully. So one of the things I would like to do, I would like to actually dump the image of the font as a PNG format, just to see if I uncompressed things correctly. I think that's actually a pretty good idea to do. So I'm going to use a separate library called stb write image, I think. It's a header only library, stb image write, yeah, this one. So if you never heard about STB libraries, so I really recommend to check them out. I'm going to put them into the description in here. Just go check them out. They are absolutely beautiful. And I'm going to grab the one that is capable of writing images in particular formats. You can just grab them as a raw file and you just copy paste it to your project. Right, you just copy paste it to your project. And the way you integrate with that library is just you include it, seriously. stb image write, you just include it, but on top of that you also have to define a special macro in here which includes implementations of the functions. So stb image write, yeah, so this one is going to be stb, this is basically what we have to define in here, right, stb image write. So essentially the reason why the heck you even need that in the first place is very interesting. It is because when you include stb libraries, stb header on the libraries, they act like headers, meaning that they do not contain the implementations of the functions, right? And you need to define a special macro for them to actually include implementations. And the reason why they do it like that is so you can control where implementations will go in terms of the translation unit, to which translation unit the implementation will go. Right, so then in different translation units you can use it as a header and not have basically several implementations of the same functions colliding together in different translation units. Essentially, that's basically the idea as I understand it. So yeah, That's why it is like that. That's why it is like that. So let's try to compile that and see if it even compiles. There's a couple of warnings in there, but they're kind of dumb in my opinion. So they're basically about conversion, but they're easy to fix like this. And as far as I know, people submitted pull requests to fix these warnings, but the original author of this library just doesn't care or doesn't have time to look into this stuff anymore, or maybe doesn't think that this kind of stuff is important because anyone can just fix those warnings themselves. I don't know. I don't blame him. I'm really grateful for his libraries and for providing them for free and the public domain. It's already very cool enough, and I don't ask for anything else. So yeah, thank you so much. Anyways, so how do you save the image? Let's see. So you have to call stbi write png, stbi write png, and let's do that. All right, so where is the main? Okay, so we have to provide the file. So it's going to be output png. The width is font width, right, and the height is font height. And the amount of components we have is 1 because it's a monochrome image and we use 1 byte per pixel. So the data is located at IMHUI font, and the stride is basically width but in bytes. Right, it's a width but in bytes. So since we use 1 byte per pixel, we can just put a font width in there and be happy with all of that. So on top of that, this thing returns an integer indicated that if something goes wrong, it will return some scary value, probably 0, right? I'm pretty sure STB libraries return 0 in case of a failure, so you can check something like this, right? So you can do something like this. And then you can say something like f std_error, let's say error could not save file. Let's say it like this. And let's also describe the reason. Let's also describe the reason. I will assume that the reason will be described in error no variable. So it's going to be file path and str error no, right? And then we're going to exit with non-zero exit code, and we want to extract file path into a separate variable. Right, it's going to be something like this, and this is going to be output png. And I'm going to put this thing in here. So as you can see, we have a reusable variable, which we can put into the function and also print in the error message, which is pretty convenient, pretty convenient. Okay, so it doesn't compile because we don't have an error no. And first of all, this thing is not a pointer. I'm really sorry. We don't have an error no. Let's actually include error no. And it seems to be compiled. All right, so if I run this program, what it should do, it should take these compressed bytes, right, that we put in here, uncompress them, and save them as PNG, right, and save them as PNG. So, and then we can take a look at the PNG file and confirm that the file was uncompressed correctly. Okay, let's try to run this program, and it works, and if it works first try, you're obligated to subscribe. How about that? Do you accept the challenge? Do you accept the challenge? Okay, let's try to run it. Okay, so it generated output PNG in a range of the size actually kind of similar to the original file. And let's open it with an image viewer, for example, a browser. And there you go. Here's the original image that got uncompressed successfully. Now you are legally obligated to subscribe. You're welcome. Yeah, so I just wanted to confirm. I'm joking, of course. All right, so our uncompression algorithm actually works correctly. I'm surprised that I managed to implement it first try. So it's kind of, yeah, because it's kind of like a pretty complicated algorithm. It's just like, yeah, it's just like we are applying 2 phases of compression simultaneously, and it still works. Surprisingly, it still works. Very interesting. Oh boy, oh boy, oh boy. Where is my soy? All right, maybe it would make sense for me to actually start some sort of a branch. in which I can do all of that. Okay, so before I commit anything, I think we need to clean things up, right? We need to clean things up. The question is when do we even call this function? When do we even call? Because this function needs to be called only once, right? It needs to be called only once. And usually, like, it just needs to be called only once per the entire lifetime of the application. So it would be better to actually keep it uncompressed in the first place. It would be just way easier to keep it uncompressed in the first place. I'm just afraid that it will take too much space and memory. But maybe it won't. I mean, to be fair, like, maybe it just won't take that much space. So this one is 41 lines. Okay, maybe I'm overthinking this entire thing. Let's actually, maybe we can just put it uncompressed, and that way we don't have to think about these problems anymore. You know what I'm talking about? So to actually keep it uncompressed, so again, I'm gonna do a very simple thing. Compressed bytes is just gonna be pixels. Right. It's just going to be pixels, and let's try to put it like that. And if I run this entire thing, so it's going to be fun again in C, char map old school PNG. All right, so what's the size? Okay, first of all, it has 8,000 bytes. Second of all, it's 514 lines, which, to be fair, is nothing, right? Which, to be fair, is nothing. This header library that we just downloaded, it's 1,000 lines of code, to be fair, which is quite surprising for a library that can. Okay, yeah, it's quite surprising for a library that can generate images, but I suppose all the things here are hard-coded like this. Okay, that explains why. Right. That explains why. So maybe we can actually maybe compress textually, like, bytes into this kind of stuff. I'm not sure if it's a good idea generally, but okay. We can always change the size of the row, if you know what I'm talking about, to decrease the amount of lines. So right now we have 16 words. We can make like 32, and it's going to be twice as small, and it's going to be pretty compact, I think. I think it's going to be pretty compact. That will require to maybe change something. So right now amount of rows is this, and if I do 32, for instance, right, if I do 32 and I rebuild everything, okay, so, and then I take this entire thing, it's going to be 258 lines. Maybe compressing and compressing at runtime is just like a waste of time, right? Just, I mean, yeah, just put it there. Yeah, I don't know why I wanted to compress it and uncompress it. Like, it makes sense for the Rust browser game, because the actual binary has to be very small. But here, like, I mean, it's just like, yeah, a bunch of crap in here, but I mean, it's a library. You're not supposed to look into that. You know what I'm talking about? Like, you're not supposed to look here. Cleverly done, Mr. Freeman. But you're not supposed to be here. So yeah, that's what I'm talking about. All right, so we can put something like this in here. And I wonder, is this actually multiplication of 128 by 64? Yes, it is. All right. So that means I can just do something like font width and font height. All right, and let me recompile this. Not really this thing. Not really this thing. Okay. Rust scares me sometimes. Sometimes Rust generates this kind of stuff. But this is because I'm not using like a cargo or anything. All right, so let me try to go here and try to recompile this entire thing. And let me see. So this entire algorithm goes away, so you don't have to have this algorithm and you don't have to call anything because the font is already uncompressed for you. It's just uncompressed, like you just really don't have to do anything. So yeah, there's a bunch of crap in here, but I mean, as the user of this library, you just don't have to do anything. I mean, I think it's a win situation. I think it's a win-win situation. All right, so, and you don't even have to do that. You see, you don't have this extra step. Essentially, you just do that. And to be fair, since it's like a static const thing, right? It's a static const thing. You don't even need to store it inside of this. Yeah, it's just like, why am I overcomplicating things? Why am I overcomplicated? Sometimes I just need to slap my face in the myself in the face to remind myself, just don't overcomplicate things. Don't overcomplicate. Just you have a font, you don't have to compress it for this specific case, just put it there. Okay. And yeah, I spent an hour overcomplicating things. Yes. Classic Zozin. Classic Zozin. All right. So if you try to compile this entire thing, it's not gonna even work properly because you don't have this kind of font anymore, but you now have this kind of font. And there we go. If you check the final thing in here, it should show the original font. We just keep it uncompressed. Okay, makes sense to me. Makes sense to me. All right. So, but now we need to be able to render. We need to be able to render this font. How are we going to be rendering it? So first we need a way by a character to find the font to find the character in the font. You know what I'm talking about? Right, let's see what we can do. We know that the size of the font is 128 by 64. Right. So, and we also need to know how many rows and columns we have in there. So let me actually open it in Chromium yet again so I can count all that stuff. So amount of rows, 1, 2, 3, 4, 5, 6, and I'm gonna count this as a row 7. So this is how many rows we have there. Define font rows 7, and the columns is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. This is how many columns we essentially have. It's 18 columns. All right. And because of that, the font character width is essentially font width divided by font calls, but that may not divide properly as far as I know. And because of that, as far as I know, there is like a padding in here, right? Padding takes into account the indivisibility of width by amount of columns, as far as I know. So the character height, right? The character height is basically font height divided by font rows, and there we go. So the cool thing about this sprite sheet is that the characters are sorted from left to right, top, bottom in their ASCII code order. So the first one is a space, and if you take a look at the ASCII table, right? So space, where does space start? So there's escape, there we go. So it starts at here. So the first one is space, the first one that is displayable, and the last one is tilde, right? And if you take a look at it, the last one is tilde in here. So basically what you need to do, so this is the decimal, you need to check that your character is between 32 and 127, and the ASCII code essentially determines the index in this particular table. All right, so let's define some sort of a function that, given a character, will give you some sort of like a rectangle or position where this entire thing is located. I'm just thinking, what exactly it have to return to you? it can return the absolute position within the sprite sheet. It could be something like that. So essentially it's going to be a function, right, that accepts, I guess, nothing in terms of the state, because the state is global anyway. It's going to accept the character, right, and it's going to return to you where that character starts, like character row and character column, right? It's going to give you row and column. Maybe column has to go first because it's going to be x and y, but maybe we just have to use x and y. Why not? But maybe just call it x and y. I don't know. And also it will return you a boolean indicated that it found that character in there, because, well, in char you can put anything in there, even an invalid one. In case of an invalid one, we should return false and never even touch these two pointers, right? All right, so how should we call this function? This is a good question. Char, oh my god, boolean char font char position. I think it's a good name. I think it's a pretty good name. Okay, let's implement this entire thing. So it's going to be implemented somewhere here. And the first thing we're looking for is that C is basically between these two things. We'll have 27, I think. Let me take a look at the ASCII. So tilde is 26, right? It has to be 26. I think this is decimal value. It seems to be like it's a decimal value. All right. So if this thing is that, we're going to do our usual thing and then return true. Otherwise, we're going to return false. All right. So then we take C and subtract 32, and that gives us the index. That gives us the index of that character in that table. So to get x, and another interesting thing, if user actually provided null in here, that means user doesn't care about this component, so we should not provide this component. So the way we're going to handle it is the following: if x is provided, only then we're going to provide the x, right? So x is going to be equal to index, right? And since it's x, it's basically a mod, right? It's basically a mod of font columns. All right, that's cool. So now if user provided y, y is going to be actually this thing, division of font colors. That's it. So that's the way we find the absolute position for this thing. That's the way we find the absolute position for this thing. All right, and now the time has come to actually render this entire thing, I suppose. Somehow, and the question is how we're going to render all of that. So essentially we need a special function that accepts the state of the UI, right? It accepts the state of the UI. Also, it should accept the position where we want to render something, right? It accepts the position where we render all of that, and it should accept the character that we're trying to render. So essentially what this function will do, it will query this character in the font and then iterate through the pixels of the font and render those pixels with triangles as we described at the beginning of the stream, right? Because in our case, we can only render things with triangles, right? We don't have any other way of rendering anything. So how should we call this function? Let's call it something like this, render char. Yes, so I think it's a pretty good name for this thing. Render character, just render character, just render character. So to render a character, we'll need things like fill rect. So I think I'm gonna actually put the implementations away here, so all of that is available in there. All right, so first thing we want to do, we want to grab the actual position in the font, right? So it's going to be X and Y, right? If font, let me grab this thing. So we provide the character, we provide the pointers, right? We provide the pointers to these things. And what's interesting is that if everything is successful, we're going to work in here. But if it's not successful, what do? What if somebody provided a garbage as this character? What should we render instead? Well, the idea, I think, is going to be very simple. We can actually call ourselves recursively, not really recursively, but sort of recursively, setting the character to question mark. It's kind of dangerous, but essentially if there's incorrect character in here, we're gonna do another round of rendering, and we're always gonna render with the correct one. Know what I'm talking about? Right, so yeah. It's kind of dangerous, but I mean it should work because a question mark is the correct character. Anyways, so here is the location, right? So here's the location, so we need to start iterating each individual pixel of the character. Okay, how are we gonna do that? Maybe I'm gonna call these things like x0 and y0, right? Because I want to use x and y for the iterators. So it's gonna be y. We're gonna iterate them by rows. Starts with 0y, less or equal, actually less 0y plus font height. Font character height, I think. Yeah, font character height plus y. There we go. So then we iterate x. It starts from x0, x less than x0 plus font character width plus x. There we go. So we are iterating the pixels. We are iterating the pixels. So, and what's the size of each individual pixel? Okay. So this is the position. This is where we start. So do I have my paint open? Do I have my paint open? Let me see what we can do in here. So essentially, position starts at left top corner, and we're iterating pixels of the character like this: left, right, top, down. And what we need to do here, we need to check if one of them are white or black. If they're black, we're ignoring them. If they're white, we're actually going to be rendering them with triangles. So if font yx is going to be 0xff, all right, maybe we can even do something like greater than 0, right, just in case there is some garbage in there. Right, greater than 0. We just need to call fill rect that fills the rectangle in here. Okay, so we're just literally rendering everything pixel by pixel. So the pixel starts at what? This one is very interesting. So this is the position at which we need to render everything. So we take this initial position and we actually add x multiplied by font character width, and we take y plus y multiplied by font character height. All right, and the size of a single thing in here is going to be vec2 font character width, font character height, and the color. Maybe we should provide the color with which we want to render the character. Why not? So it could be RGBA color, because why not just provide it? I mean, yeah, sure. And let's just provide it in here. There we go. That's literally it, as far as I can understand. So this is the position, this is the size, and this is the color. It will be a little bit easier to express all of that with pointer arithmetics. Vector arithmetics, not pointer arithmetic, what the hell I'm talking about. Vector arithmetics, but I think it's good enough as it is right now. So I think I also need to update the signature of this function. Render character, so I'm going to put this thing in here, and there we go, there we go. All right, so let me try to recompile this entire thing and see if it compiles or not. Excuse me? What are you talking about? Expected equals... Thank you. See? Very cool. This is the most readable error C ever actually gave me in my entire life. Like, what the fuck? Oh boy. Okay, so... Excuse me? Is this because of that thing? Oh! I see. Is that because I forgot a semicolon in here? I guess it is. Holy shit. Okay, subscribe. Okay, so this one is slightly different, like font width plus X. Right, so this is how it has to be, and this one is actually P. I cannot get over it. I literally cannot get over it, like how bad it is. Look at that. So let me try to reproduce that problem one more time. Like, you forgot a semicolon in here. You just forgot a semicolon. This is what the compiler tells you. Wait, what? The fuck? I suppose classic GCC. Is it somehow different with Clang? Yeah. Okay, Clang is a little bit slower, but... Okay, Clang won. Congratulations. Clang just won over GCC. We're using Clang then. Because the fuck is this? But also I'm using a quite old GCC, so maybe in the latest GCC they actually fixed this problem, but I don't know. Alrighty, so I guess we have an algorithm that can render a single character, which is quite goddamn cool, isn't it? I think it's goddamn cool. Let's actually try to render it, render the character. So where are we rendering the buttons? Okay, so here we're rendering the buttons, but I think I'm gonna actually remove it. So we're not rendering any buttons anymore. Let me rebuild everything and run the application. It should have like an empty screen. So here it is. And now let's render just an image. Just an image. Render character. Okay. So here is this. The position is gonna be, let's put it somewhere like around 50-50, right? I don't know if it's going to be visible or not, but let's just try it. So here is the position, and what's going to be the color? RGBA red. We're going to use the color of communism, my comrades. And what's going to be the character that we're going to be printing there? Let's print E, right? E. Okay. Should work. Let's see if it works. It doesn't, because I have to actually take it by a pointer, and I tried. Okay, let's see what exactly went wrong. Let's see what exactly went wrong. So I tried to find the position, okay, of the character. So maybe I found incorrect position first of all. So this is that. If I provided X, it's a mod of font columns. All right, it is mod, and otherwise it's a division of font colors. So far so good. Don't see any mistakes in here. All right. Then we're starting to iterate this entire stuff. So I'm iterating from that to that. I could have actually implemented from 0 to font char and then calculate the actual X myself, but whatever. So then I'm taking the thing in here, the actual pixel, and if the pixel is there, oh, I see, because I'm using the coordinates of the font sprite sheet, and I have to use coordinates of the offset from the position of the character. Okay, so that only confirms that I have to iterate from 0 to font char height, and maybe I should call this thing something like OY for offset, right? So this is going to be OY. It's like yo. Let's actually call it yo. Yes, it's a Y offset, yo. And this one is going to be Right, so, and this stat is gonna start from 0 up font character width, right? It's not ont, it's a font. Right, so we have a yo and mwah, a yo and mwah. And in here, what we have to do, actually, we have to probably construct like the absolute positions. It's gonna be basically x0 plus x offset, and y is y0 plus y of... This is absolutely horrible decision. So if there is a font where like 0 and O looks similar, you're gonna have a hard time actually reading that, especially if we rename it to like capital O. But I mean, again, if you're a programmer and you're using a font where you cannot distinguish zeros and O's, maybe you're using a wrong font. Like any programmer should use the font where you can distinguish 0 and O's and also else, ones and I's. If you're using a font where these three things looks the same, you're using a wrong font, my friend. Seriously, you should reconsider your life choices. So these three things should be different, and that's very, very important. So there we go. All right, so these are absolute values, and we take this thing, but in here we have to use the offset values, right? We have to use the offset values instead of the absolute ones. And now that finally makes sense. All right, okay, I'm super happy. And did that recompile anything? That didn't really recompile anything, and that didn't even fucking work. I think I found a mistake in my head. This function is supposed to return coordinates, absolute coordinates within the font sprite sheet. But what it returns the grid coordinates. So what I need to do in here, I need to multiply this entire stuff by font character width and this entire stuff by font character height. I think that's what the mistake. All right. Okay, and something went wrong. We ran out of vertices all of a sudden. Usually this kind of shit happens when we don't clean something. I think that's what usually happens in here when we don't clean, or maybe we just generated too many of them. I cannot imagine generating too many of them, to be fair. But yeah, so essentially we overflew all of our buffers of vertices, and that means that the condition somewhere actually, I think the loop actually became infinite. And it actually kept pushing things into it. Let me see. Oh boy, oh boy, oh boy, oh boy, oh boy. Where is my soy? I cannot imagine like generating so many. Okay, I think I'm gonna make a cup of tea. You probably already noticed the mistake, but I'm actually, from my perspective, I can still can't see. So let's make a cup of tea. Let's make a small break, and then try to find the error in here. All right, drinking my Earl Grey yet again. One way to check for sort of infinite loops would be actually remove this condition. So there's no infinite loop in here. Wait, I'm an idiot. I intentionally made the buffers of triangles very, very small, like 69 or so, because I made it as a joke. Like the actual buffers have to be pretty big, like at least like 1K of them. Okay, there is no mistake in here. So it felt like, so the buffer overflew, so I thought that maybe there is an infinite loop somewhere that keeps pushing triangle. No, it's just like buffers were small, and I completely forgot about that. And I didn't even have to make a break. Right, I only started to prepare my tea and it just hit me. Yeah. My buffers are small. That was the problem. E. Yes. E. Absolutely. Fucking epic, mate. We rendered E. So before we continue, let's make a cup of tea. And then we can try to integrate it into buttons. My ultimate goal is to actually have buttons with the text on them. That's my ultimate goal. If we manage to achieve that today, I'm gonna be super happy. Super happy. I don't have a clipper to actually seal this thing, unfortunately. God damn, bro. Alright, I'm gonna go to the kitchen very quick, and you know what, maybe I'm gonna make a small break because I also kinda wanna pee. Not gonna lie, but I'm super fucking proud that we managed to render E. Holy fucking shit. Can we render more things in there? Like, for example, I don't know, Q. We can render Q. That's a pretty good looking Q. Not gonna lie. All right, so let me put a small break. So we're gonna have 3 minutes break, and yeah. Let's put some music on. Let's listen to some jazz. Alright, let's make us back and have fun. You can skip it. I mean, you're watching it in a recording. Yo, welcome back. So, maybe there is a way to pause the recording of the OBS So I could, when I go to the break, I can just pause it and unpause it. But maybe not, I don't know. Like, I don't want to have any editing, even such rudimental one, because it just makes it feel unnatural. I don't know why I care about this kind of stuff, but for some reason I do. So do I still have enough space for the recording? I think I do, so everything looks okay so far. Alright, so I'm waiting for my kettle. So one concern that I have is that the letters look pretty big. The question is, why the fuck they are so goddamn big? That's the question I have. In the original font, they're actually rather small. But in any case, I think I know why. It's because I'm blowing up the pixels. Yeah. The screen coordinates are in pixels. I don't have to do this thing, actually. I just don't have to do it. Yeah. The original font is actually quite small, and it, yeah, I think, and this one actually has to be 1 by 1. Yeah. Yeah. So it's gonna be F and F. And yeah, now we're talking. This is how it's supposed to look like. It has to be very, very, very small. So my tea is ready. I'm gonna go to the kitchen to pour myself a cup of water, and I'm gonna be back. So, and then we're gonna implement some sort of a scaling. So we're gonna be able to provide a factor by which it's gonna be blown up, and we'll be able to customize this kind of stuff. Okay. All right. So the scale factor has to be some sort of a floating point number, I think. So here is the position, and we might as well accept the scalar like this, right? And if we go down, this is where we're gonna have it, right? And then this is where we pass it, and essentially it's about just multiplying it like that. I kind of already had a scalar, but yeah, so I just brought it back. Okay, so here I have to provide like either 1 or more. Actually, yeah, I think it has to be here. Yeah, now we're talking. Now I can make it twice as big, or 16, for instance. There we go. So now I'm capable of scaling this entire stuff. Beautiful, absolutely beautiful. Mein Gott, mein Gott. All right, so what do we have in here? We have some stuff that we probably don't need anymore. Uncompressed font, we don't have this function anymore. So I guess the next logical step is to render a text. You can render a character. The next logical step is to render a text. So let's implement something like void imhui render text. Right, you take the state of the UI. Right, you take the state of the UI. You take the position at where the text starts. You take the scaling and color, right? And then instead of character, you're actually taking the text itself, right? You're just taking the text itself. So, and it's basically as simple as repeatedly calling this thing shifting the position. It's as simple as that. Nothing particularly special. It's a mono width font, bitmap mono width font. It doesn't require any sophisticated logic. It doesn't have a built-in Turing complete language or anything like that. Am I right? So let's actually save the size of the font in here. So it's going to be n strlen text, and we're going to be iterating from 0 to n, right? Something like this. And we're going to be calling this function, and the position is going to be different every time. So it starts at x and y, but then depending on the scalar, right? Depending on the scalar, it's going to be shifted like so. It's going to be font character width, and also it has to be multiplied by I. Right, there we go. So that's how we're going to be shifting all of that. So the scalar is going to be this, the color is going to be this, and the character is simply going to be text I. There we go. Simple as that. Believe it or not, it's as simple as that. You just repeatedly call render char, shifting the position at which you're rendering all of that. Okay, so let's try to apply that in here. So it's going to be render text, and now let's try to render something like hello world. And again, if this works first try and you will see a red hello world on the screen, you are obligated to subscribe. It is the law. Let's see if you are obligated to subscribe. God Cooler. Subscribe now. Sorry. Isso. Какой fucking this, mate? Mein Gott. Staged. It's not doing that live. It's edited. Okay, so now we're capable of rendering text. That's pretty cool. And we can render that text with different colors as well. For example, with green. So now it looks like Matrix and shit. That's pretty pogue, I'm not gonna lie. That is in fact very, very pogue. So the next logical step is going to be adding these things as labels for the buttons, right? So at the beginning of the stream, I showed that we have 5 buttons, but unfortunately buttons, yeah, as you can see there, like they're supposed to have some sort of a text, but they just don't. Because we didn't have any ability to render the text, but now we do. So we need to integrate that ability to render the text with the ability to render the buttons, and we're gonna have a pretty cool UI library that only handles buttons with text. But it's something, and we made it ourselves from scratch. So the only thing we used OpenGL, but I mean library itself is actually does not depend on OpenGL, right? It's completely decoupled from OpenGL because you render into a buffer of triangles rather than like calling OpenGL functions. It's completely decoupled. We don't have to think about that. So we can still claim that this library is implemented from scratch. And it is potentially integratable into DirectX, so that means it potentially works on Windows, and it's potentially integratable into Metal, which means it's potentially working on macOS. As a matter of fact, maybe I can steal something from IMGUI to make it work on Windows and macOS, because IMGUI actually has a lot of examples. So let me show you what I mean. So yeah, there we go. So they have a lot of integrations with different libraries and different graphics API. Vulkan OpenGL 2, look at that. Glut OpenGL 2, GLFW OpenGL 2, GLFW OpenGL 3, Vulkan Metal, SDL DirectX 11, and so many different things. So it's just a lot of different integrations. You can just steal that code. I mean, according to their license, what is the license of this library? I think it's MIT. Yeah. Okay, so that means I can do whatever I want with this source code as long as I don't claim that I made it. So that's actually fine. Our library is also under MIT, so you're also free to do whatever you want with our library. Anyways, I think the time has come to do a committee and maybe even pushy. We don't need this kind of stuff anymore. It's just experimental garbage. And I think we're working on a very specific to-do in here, right? The image buttons don't display its text, so this is precisely what we're working on. So let's create a separate branch called button text. Right, there we go. So we have a le button text. And let me see what we can do in here. So let me maybe remove this entire thing. So I'm HUI button, and let me go in here. So now, do we even use ID? We do use ID, so I don't know why I'm actually marking it as void. It doesn't have to be void. All right, so we fill the rectangle, and after we filled the rectangle, what we have to do in here is we have to render text. Right, so let's just render text. By the way, let me go back in here and steal a little bit from here, like this. Just copy pasting. So I think we're gonna render text starting from this position. We're gonna actually do that in a very dumb way, right? So we're gonna start at the left top corner of the button. It's gonna look very silly. So then we're gonna have something like I'm HUI button text scale, right? And then we have something like I'm HUI button text color, right? And here we have the text. I think it's called the text. Yeah, it's literally called the text. Okay, that's cool. So now we'll have to define these two things: text scale and text color. Scale and color. So let's define this thing like that. So what's going to be the scale? Let's actually keep it 8. What's going to be the color? I don't know. Let's make it white, I guess. Okay. So let's see if it's going to compile or not. So we don't need that stuff anymore. And something went wrong because it doesn't have to be a pointer, and it still crashes somewhere here because we don't have enough vertices yet again. Are you serious? Oh my god, we might not have enough vertices because we're junior. Yeah, okay, here's another interesting thing here. So let me just increase the amount of vertices, like maybe multiply the entire stuff by at least like 8. Right, let's multiply it by 8, and I think we should... Yeah, there we go. So I told you it's gonna look silly, okay? I told you it's gonna look silly. One of the things we can do is maybe reduce the scaling a little bit. Right, yeah. So we can keep reducing the scaling. Now it looks more or less reasonable, right? So now it looks more or less reasonable, and you can click on it. Okay, here's the thing. We are using indexed rendering of the triangles, right? We're using indexed rendering. What that means? That means the triangle is defined not as sequence of vertices, but as sequence of indices in a separate array of vertices. What that enables us with is a pretty efficient way of representing triangles, right? So if you want to render a quad, right? If you want to render a quad, you can only render it as 2 triangles, like this. Right, and essentially what we do, we put 4 vertices like V0, V1, Zulu, V2, and V3 into separate array. V0, V1, V2, V3. So these are the vertices, and then we have the array of indices. And this array of indices basically has 6 vertices. 6 vertices for 2 triangles. Right, and the first triangle is going to be V0, V1, V3, V0, V1, V3. The second triangle is going to be V0, V3, V2, V0, v3, v2, and as you can see, we reuse a lot of memory in here, right? We reuse a lot of memory, so that's precisely the reason why we're using like indexed rendering. If you don't know about OpenGL indexed rendering, I recommend to Google it up. But here's how we render the pixels. So imagine that you have like something like this. So you have 3 pixels in here, and maybe you have another pixel in here, and maybe this is your H, right? This is your H consisting of 7 pixels, right? So the thing is, we're only reusing the vertices within a single pixel, right? As we generate 2 quads in here, so the adjacent sides of the quads don't really share vertices. So these 2 vertices are not shared between these 2 quads because we didn't implement that. So the reason why it works like that is because this is the easiest way to implement it, and I wanted to implement a very simple algorithm on the stream, and that's exactly what I did. So implementing it in a more efficient way is going to be actually a separate issue. So we're going to have an issue where we'll try to take this sequence of unconnected quads and connect them together to actually reuse some of the vertices, and that will be actually kind of interesting to explore, right? We'll have to come up with an efficient algorithm to do so, but right now there's a lot of like wasted memory, and that's why we have to allocate huge buffers, right? We have to allocate huge buffers, like 8 kilobytes. It's not even kilobytes, it's actually more than 8 kilobytes, because a single vertex is actually more than just 1 byte. It's pretty huge buffers, not gonna lie. And I wonder, yeah, so right now we have to render a lot of triangles to just render this entire thing. And well, you would probably say that we could have rendered it as a texture, but again, we have a cross-platform way of rendering our UI, right? So the only thing we're allowed to do is render triangles, so we can easily integrate with any graphics API, right? Because you can render triangles in any graphics API you want. The thing I'm curious about is how many triangles do we even, like, how many vertices first of all, and how many triangles we have. So after we rendered all of these things, right, so we're about to render this entire stuff, and maybe somewhere in the render we could print something like vertices ZU, so this is the vertices, I am HUI, so where is my structure? Oh boy, where is my, so okay, so this is a vertices count, and then we have triangles, and maybe I'm gonna even make it a little bit pretty and put an extra space in here so the numbers align. Look at that beautiful alignment, oh my god. Triangles count, there we go. So, and maybe after that I can just crash, because I don't want to, like, you know, spam the entire output. I just want to know the amount of vertices and triangles. So let's try to run this entire thing. It didn't compile because this is not a pointer. Thank you so much, C. And okay, 1620 vertices and 810 triangles. Not that much, to be fair. Not that much. I think, how many triangles modern games usually render, like per frame or something? I think they render a lot on the modern hardware. So yes, you need a modern hardware to work with this UI, because you need to be able to render a lot of triangles at 60 FPS. Yes. Can your web do that? I don't think so. Anyway, so let me actually make it a do. Render text, maybe even the render character. So let me see. To do I'm HUI render char. To do the vertices in the adjacent. How do you spell adjacent? Adjacent I think it's yeah, adjacent, a J dollar and a J cent. I'm sitting alone in my room, offline, laughing at my own jokes. Tell me if this is not a definition of insanity. Holy fucking shit. Anyway, so the vertices in the adjacent pixels are not reused via the indexing. Okay, so this is going to be our to-do. To-do, to-do. All right, so this is what we have. The thing I want to do now, I want to align the text vertically and horizontally so it looks good. That's the goal. The goal for the text to look good. To be fair, I think the text on such a button color, on such a horrible button color, because I do realize that the button color is absolutely horrendous, but this is because I want it to be bright and visible because we're testing things out. This is a testing color, don't laugh at me, okay? So what I'm going to do, I actually I think it's actually going to be more visible if the text is rendered in black. Let me give it a try. Yeah, I suppose. I think it looks a little bit better. I do think so. And I do like that the button actually reacts in a button way, right? So essentially it highlights when I hover over it, and I can click on it, I can hold it, but I can press it outside of the button and it doesn't trigger. It only triggers when I unpress inside of it, so it's real button. It is in fact a real button, really like that. Okay. Immediate UI, everyone, immediate UI. So how can we align shit horizontally? That's a good question. So we know the height of the text because we know the height of the character and we know the scale. So we can just adjust the position so everything is aligned at the center, right? So at least vertically. So then we can think about horizontal stuff. All right, so let me go here and IMHUI button, le button, right, here is le button, and in here, so what's going to be the height? Const float text height. So here's the text height. It is equal to font character height multiplied by the IMHUI button text text scale. Le button text scale. All right, so that means that in here we have to do a custom position. So in terms of X, we're not aligning anything in X, but in terms of Y, it has to be plus IMHUI button size Y, but half of it. So we're adding half of the button height and subtracting half of the text height. That's essentially what we're doing, and I think that should align everything vertically. You know, this is a completely unsolved problem in CSS, but I think we can manage to solve it at least in C. Right, we should be able to solve it at least in C. All right, so I think we managed to solve it. Look at that. Isn't that amazing? I think it's good and fucking amazing. It's aligned, you know, vertically. How about horizontally? Well, horizontally, it should be pretty much the same. It's just we need to have something like text width. And text width is slightly different. It's font character width multiplied by text scale, but also by the amount of characters that we have in the text. You see? So we need to take strlen and text, and there we go, we have a text width. So, and essentially we have to do a similar thing in here. We have to add button size button size X, half of it, minus text width, half of it, and that will make it align horizontally as well, more or less. I think it is kind of aligned horizontally. I think it kind of is. What do you guys think? So, you know, it would be kind of cool. So it probably should also handle the overflow, right? So if we make it super big, it still will align. Yeah, there we go. You cannot see it, you can only see TT. You can only see TT, right? So it's a TT buttons anyway. So if we change the text color like this, so this is the buttons, the text of the buttons. It's aligned, you know, it's centered horizontally perfectly. I'm not really sure what to do if the text doesn't fit into the button, but I think I'm gonna just ignore the fact that sometimes it doesn't fit, and maybe just create a separate to-do for fixing that later. I think that's gonna be a good idea. I think it's gonna be a good idea. So I also wanted to do something, but I forgot what I wanted to do. Yeah, I wanted to create a to-do. Yeah. Button. Okay. IMHY button does not handle the situation when the text is too big to fit into the boundaries of the button. That's a pretty big text. Just like the problem that we described. Okay, and I suppose we did it. We just added support for the text, for the buttons and stuff like that. And it took us 2 hours, precisely. It took us 2 hours. That's actually pretty cool. Huh, would you look at that? I'm so productive when nobody is, you know, backsitting and bike shading. It's amazing. Alright, so I kind of wanted to change the style of the buttons. I don't know, make them feel like they actually, how to say that? They're actually pressed. Basically give them volume, right? You can give them volume by slightly offsetting them when they're unpressed and offsetting them back when they're held, if you know what I'm talking about. We can do something like this. Okay. So let's do a committee. Let's do a committee. Surprisingly, there's literally no changes in main. Huh. Not bad at all. So it's just like magically text appears on the buttons. All right. Make IMHUI button display text with a simple bitmap font rendering, and it fits into the entire message. Okay, so I'm gonna push that right into the ribbon. And what I want you to do, I want you to try to give the volume to the buttons. Right, so right now I'm not really sure if the volume is going to be that visible if the buttons are stuck to the side, so it would be kind of interesting to make them unstuck a little bit. We can try to render them somewhere to the side. I think in the IMHUI begin, we are initializing last widget position, and this is basically from this position the buttons will start laying themselves out. So we can actually start doing them from 100 and maybe like 10, and they're going to be slightly in a different position. So maybe in terms of height it's also going to be 100, right? So yeah, there we go. So now we can offset them, and offset is going to be actually visible, which is good. I think it's good. All right. Alrighty. So how are we gonna do all that? I'm HUI le button. So if it's active, it's actually held, right? If it's active, it's actually held. Maybe we need some sort of an offset. We have a caller variable that we modify depending on whether the button is active or not or something like that. And maybe we need to have something like an offset variable here too. Right, so it's going to be offset and it's going to be a usual MHUI button offset. Right, something like this. Right, and if you're active, I guess what we're gonna do, if you're not active actually, right, if you're active in here, offset will just become 0, 0, right? Yeah, the caller will become active and offset will become 0, 0. And then we're using this offset somewhere here. Vec2 px py plus offset x plus offset y. I really need to implement the vector arithmetics for this kind of stuff, but I'm too lazy. Sorry. Okay, so it's going to be plus offset, and then I can do something like there we go. So now we have an offset. But we need to also define that offset. I also need to define that offset somewhere. So here's a button offset, and let's say that offset is going to be around 10 pixels. I think that's a pretty good offset for a button to give it a little bit of a 3D effect. Let me show you. Okay. I think I did the funky wacky. Okay. First of all, I didn't think it has to be that big. It has to be like around 5, right? It has to be around 5. And what do we do with it? We actually add it, and when the entire thing is active, it have to actually... Oh, I see. We have to subtract the offset. I think we have to subtract the offset in this particular case. Yeah. All right, and now I'm actually look, chat. I'm actually pressing them. Holy shit! It looks so cringy. This is the cringiest like pricing I've ever seen in my entire life, and this is because the offset is too big. So we can set the offset to like maybe 2 pixels. How about that? How about some 2 pixels? And yeah, of course I need to do something like, yeah, that's already better. That's definitely better. We can actually put something behind the buttons at offset 0 to sort of give it the volume, the visible volume. This gives us like an interactive volume. But we can also add like a visible volume, if you know what I mean. So we have a text button caller, and I don't even know what to put in there. Let's actually see. So so here we render one rectangle with offset, and we can render another one without the offset. And here is the button size, and the color that we can use is IMHUI button color background, maybe color base, right? It's going to be a color base, and where our colors are defined. So it's going to define IMHUI color base, and it's going to be sort of like a grayish color. I think we're going to keep it like very grayish, and this one is going to be something like this. There we go. All right. And can you even see that? Oh shit, you can. Nice. Maybe it has to be a little bit brighter because it's too dark. Let's make it like around 4. I think it's gonna be, yeah, now it's more visible. So now you can see this sort of base. It's still kind of cringy. It still looks dumb, and especially with this font. But yeah. But it is a like button with the text, and it's like 3D or something, and it just it's like you can interact with it. So that's pretty cool. So let's make a separate commit in here. Give the button more volume, right? Give the button more volume. Let's push that right into the repos. So, and let's create the pull request. I didn't think pull request makes sense in this particular situation because we don't have a continuous integration. Maybe we'll need to set up continuous integration for this project, but it's not that important of a project. It's just like farting around. So yeah, it was officially merged. You can find the source code to this project in the description if you're interested, and here is the result of today's stream. We have buttons with text and they're 3D or whatnot, and you can interact with them. So I guess that is it for today. Thanks everyone who's watching me right now. I really appreciate it. Have a good one, and I see you all tomorrow. I have no idea what I'm going to be doing tomorrow. Whether I'm going to be streaming tomorrow. Probably I will stream tomorrow. I cannot not stream. It's just like it's a part of me that I cannot get rid of. I must stream. So yeah, I'm probably going to be doing something tomorrow. Stay tuned. Subscribe to this channel. Smash like. And the usual jazz. Hope you found this programming session interesting, and I see you all tomorrow. Love you.